Good morning or good afternoon, ladies and gentlemen, and welcome to today's webinar. My name is Kiki Noel from the Business Review, and I'll be today's host. I'm delighted to have with us today Freeslate, who will be discussing development of an automated feedback loop to support reaction screening. We are joined by Kristin Price, who is the Principal Scientist at Pfizer. So without further ado, please allow me to welcome Kristin, who will start the presentation.
Hi, my name is Kristin Price, and today I'm going to be telling you about the development of an automated feedback loop to support reaction screening. As Kiki mentioned, I work at Pfizer. I'm in the Chemical Research and Development Group, and I work in a subgroup that focuses on technology development and reaction screening. We do all of our screening for process research, which means we're looking typically at how to best run a reaction. So we already know what we're making, but we're trying to figure out the best way to make that. And we support reaction screening for both the early and late development portfolios, which means we see all ranges of chemistries and many different kinds of projects with different material availability. The focus areas for our group are amidations, cross-coupling reactions, and this includes both traditional palladium as well as the non-base metal catalysis and acid-base catalysis. Over the past couple of years, we've been transitioning from more small manual screens to larger automated screens. So going from screens that were typically less than 50 vials on a first pass to large screens that are usually greater than 100 vials, at least on the first run. To support these larger runs, we have two high-throughput screening platforms. One is the ChemSpeed Swing, and the other is the Freeslate Core Module 2. The Freeslate Core Module 2 will be the focus of my talk today. Once we've run these large high-throughput screens, we typically follow up with a second round of screening and validation. I'm going to start today by giving an introduction to the Freeslate Core Module 2 and its system capabilities. You'll notice on the back left is a circular hole. This is actually the entrance to the balance that's on deck. So unlike systems where gravimetric dosing is done by difference, where only the bottle of reagent is weighed, here we actually move vials to a balance and weigh into them. What you'll see, the metal cylinders you see in the front are actually the solid dispensing hoppers. They're available in both the large size, this is 25 milliliters, but they also come in a smaller 10 ml size. And these will be held with a gripper arm over that balance to dispense into small vials. We have 3 different bays, so that allows for 3 different temperatures and unique stir rates. The range on these bays is from about -10 degrees to about 100 degrees, with stirring from about 0 to 750 RPM. The deck supports a large number of different vial sizes. Typically, we use 2 ml vials to do our reaction screening. 96 well plates are available, but the 2 ml vials allow us to basically go between our 2 platforms as well as directly onto our analytical equipment without ever transferring our reaction mixtures. And what you'll see is on our deck we also have 8 ml vials and 20 ml vials. Typically the 8 ml vials or the similar 4 ml vials are what we use to do reagent dosing. One thing that's unique about our Core Module 2 and that allows us to do the feedback loop I'm going to tell you about is a custom LC injection valve. So the inject valve on the back of the deck is actually connected into an Agilent 1100, which is sitting just outside the nitrogen enclosure on the other side of the Core Module. We do have this Core Module inside a box. It's nitrogen filled. It's not a full glove box, so it's going to limit water and oxygen content, but not get it down low enough to do extremely oxygen-sensitive chemistry. And off to the right, you can see just a peek of the bottles of off-deck sources. I'll refer occasionally to off-deck sources. These are bottles of reagent, typically they're quench solvents in our case, that are actually fluidically run into the system through a valve and that can be dispensed on deck, which would be any of the vials that you see in front at any time without having a vial on deck of that solvent mixture.
To continue on with the system capabilities, the right arm, which is the one pictured in the previous slide, as well as in this picture, has a gripper, which you'll see here. And those actually allow you to move vials around the deck. They allow you to move vials to the balance or vials between plates. It also has a piercing tip needle. This one's 22 gauge, so it's fairly narrow, but it allows access to on-deck reagents, which are just a vial of reagent, or those off-deck sources I was speaking of, the large solvent bottles, which are kept outside of the box. The left arm, which I don't have pictured here, has a large gripper that moves those solid hoppers I was showing, which are both 25 mil or 10 mil. And the single tip needle, which is 16 gauge, so significantly wider. And this only has access to reagents that are on the deck. But what's great about the 16 gauge is you can access slurries, which might be too thick and would clog the 22 gauge. We also have the on-deck balance. You'll notice this is a different view. There's actually a camera in the balance, so you can see what's going on and make sure everything is where it's supposed to be. But this allows us to take vial weights, as well as doing gravimetric solid dosing and liquid dosing. And one of the nice features is that you can set tolerance on all of these gravimetric additions to really customize them for your application. You don't need to remember the software for this talk, but I just wanted to give a quick introduction to the vocabulary associated with the software so that when I speak about it, you'll know what I'm talking about. The first is Library Studio. Library Studio is what allows us to build the recipe for the run. What are we adding to each vial? How fast are we stirring each vial? How long are we stirring each vial? And what temperature do we want the plate to be? Automation Studio is the second piece of software, and this is what executes that recipe. Automation Studio allows you to control the robot arms and the deck. This is what's actually setting the temperature and moving the vials around the deck. And then finally, PolyView, which captures all the data from the run. When we're running these high throughput screens, we're running a large number of reactions on very small scale, milligrams of material each. We need to have confidence that every vial is being made up in a reproducible, precise, accurate way so that we know if something shows a hit, it's because the chemistry worked. And if it doesn't show a hit, it's because the chemistry failed, not because a reagent wasn't added that was supposed to be added or too much of something was added that wasn't supposed to be. So we went through to do a significant amount of testing on the different kinds of dosing. And we actually started with liquid dosing because with initial testing showed us that there was some variability. And this led us to a full statistical study. In this study, we considered 3 different variance components: vial-to-vial reproducibility. So this is saying 2 vials next to each other, how similar are they when the same amount and type of liquid is dosed? Is there any variation within a sequence? One of the features of the system is you have multi-aspirate mode, where essentially the syringe will fill up with multiple dispenses worth of reagent and then put it into multiple vials. So it's a single syringe pull for multiple dispenses. And so we wanted to look at that sequence. And then the other thing is repeatability. So is one plate the same as the next plate? And so for a variety of different volumes, we did 3 replicates of 48 vials, and the vials are basically weighed empty. We dose water in, and then the system is used to weigh them again. So we can measure exactly how much is dosed by the weight of water present in the vial. And we tested with both the 22-gauge needle and the 16-gauge needle. There's a lot on this slide, so let me walk you through it. I'm just giving a single example of our analysis of variation in dosing. So let's take a look at the graph first. Each point is actually 3 replicates. On some, like the one that the black arrow is pointing to, it's very obvious that there's 3. Some, the 3 are very much overlapping, but they are all there. The y-axis here says percent bias. That's not a traditional measure for most chemists, but essentially it's saying how different is the weight that's in the vial from the weight that's anticipated. So it's basically your percent difference from your target value. So minus 10% bias would be 10% low on what should have been a 50 milligram dose. So x-axis here is just saying which vial position are you in the top row, and then which row are you in a single plate on the bottom row. So the blue points here represent 1 vial at a time dosing. The syringe pulls 50 microliters, doses 50 microliters, washes, and then goes to the next vial. And what you'll see here is we actually have the precision is very reasonable and the accuracy is acceptable. It's less than 10% bias all the time, and it's very reproducible. The challenge with single dosing is that it can be slow because you're washing after every dose. So we also looked at the multi-aspirate, which is where you have a single filling of the syringe, and then in this case, 7 consecutive dispenses. And what you'll see is that for the first 6 of those 7 dispenses, there's great precision, and the accuracy is actually really good. But unfortunately, on the 7th dispense, it's consistently off, and it's 20 to 30% off, not just slightly off. And so as a possible solution to this, we're looking at programming it so that when you're doing this multiple dispense mode, which is a lot of times more efficient for running a large screen, making sure that last dose goes to a waste vial or is returned to the source vial so that you don't have a reaction with either too much or too little of a reagent. We then moved on to look at solid dosing. And essentially, solid dosing can be a challenge on any piece of equipment, and a lot of times this is because of the solid properties themselves. Hygroscopic materials, superfine powders like potassium phosphate, for instance, or very chunky solids, or staticky solids for that matter, can be a challenge regardless of what piece of instrumentation you're using to dose solids. We actually tested with 2 solids we needed to dose for screens. The first was cesium carbonate, and we were dosing with a specification of 32.5 milligrams per vial, which is 100 micromoles. It's pretty standard for our cross-coupling screens. In this case, I used the percentage tolerance and set a 10% limit on this number, which means every vial that would be considered inside specification would be plus or minus 10% from 32.5 milligrams. And what was great is 119 vials were dosed very successfully within this 10% limit. There were a few vials lost that were outside of specification. This is very typical because as the hopper dispenses over multiple vials, you get some learning. It'll speed up as it gets accustomed to the solid and how quickly the solid doses onto the balance. Every once in a while, a small chunk will fall, and you'll get a vial that's outside of specification. This is very typical. And what's nice is the software will actually denote on the screen and graphically which vials are outside of specification, so you can remove those prior to using them in a run. with the potassium carbonate, we were dosing 138 mg, and we used a different way of setting the tolerance. In this case, we said that we can't take less than 138 milligrams, so 0 milligrams under, but we could take up to 10 milligrams over the 138. And what you'll see is it dosed very successfully with a very low relative standard deviation over 185 vials. So when we're doing this solid dosing, typically we'll do them offline. So we use the automated system to weigh out the solids for potentially hundreds of vials at a time. And then we store those in desiccators for use in screens. So we're not trying to dose liquid reagents right over these, and we're not losing vials that are outside of specification. The third type of dosing that's very important to us is slurry dosing. You wouldn't necessarily think of slurry dosing as a common thing, but for us it is. Typically we're setting 1 or 2 solvents that we may be running in our screen, possibly 3 or more. And not all of the catalysts we're using or the reagents we're using are going to be soluble in the solvents that we need to run, at least at room temperature. As a result, we rely on dosing rapidly stirred slurries into vials so that we don't have to weigh everything as a solid. Slurry dosing is significantly faster in a lot of cases than solid dosing. Our model slurry was phenylalanine and THF. Phenylalanine has very limited solubility in THF, and we looked at 3 different levels, 50 mg per mil, 100 mg per mil, and 200 mg per mil. The reason we looked at multiple concentrations is sometimes you have a very thin slurry. It might be a catalyst where you're only dosing fractions of a milligram into a vial. It just happens to be insoluble. So you have a thin slurry, sort of like a small amount of sugar stirred up in water. But you could also be dosing a stoichiometric reagent that's highly insoluble and necessitating the 200 mg per mil dose. And this is when you have a slurry that's sort of similar to paint. The dosing levels in this case were 100 microliters and 300 microliters, and we did 24 replicates at each combination of levels. A few notes for slurry dosing in general. First is a high stir rate is necessary. It's necessary to fully suspend, especially at the 200 mg per mil concentration level. So if you don't have sufficient stirring, you'll get the separation where you see solvent on top. And the other key for slurry dosing is that you have to limit the total volume, because we have sort of tall, skinny 8 ml vials, and the stirring is underneath. And so it's important not to overfill the vial so that you get effective stirring throughout the entire slurry and you don't get any layering effects. And one note for this study specifically is that all stocks were made gravimetrically, so all of the concentrations and target weights are approximate. I realize the text is slightly small on the slide, but the key here is that we're looking at the weight of phenylalanine after drying it down in a tared vial, after dosing as a slurry, versus the target weight. And what you'll see is it's highly reproducible. In all cases, we're under 3% RSD for our vials at any given level of slurry dosing. So slurry dosing overall was highly effective at all of the levels we tried. And this gave us a lot of confidence going into high throughput screens. This is an example of a standard high throughput screen on the Core Module 2. This is a screen we actually ran using a standard commercially available carboxylic acid and pyrrolidine as you need for an amidation screen. We use this screen as actually our comparison between the different platforms that we run. The first step, anytime you're running a high throughput screen, is to design it. So you choose your variables. In this case, it's going to be tertiary amine, additive, activating agent, and your reaction conditions are chosen. You have your standard reaction conditions: temperature, time, stir rate. But when you're running an automated screen, as opposed to running manually, you also have to consider your dosing type. Is something a slurry or solution? Should it be dosed with the left arm or the right arm? Should it be dosed as multiple dispense or single dispense? You also have to consider your addition order. When you're dosing manually into a small set of vials, your additions happen very, very quickly. Oftentimes, there's only minutes between your first and final addition into a vial. But when you're dosing with an automated system, it will take some time to dose through all of the reagents into all of the vials. And so you have to consider that when you're planning a reaction. This reaction was actually designed to include 144 different conditions. After the screen is designed, we create a library in Library Studio. Remember, this is just a recipe to tell the instrument how to run your chemistry. The details of each line aren't very important for your purposes, but what I'll highlight is that you set your block temperature, you set stir rates, and you're telling it what to add to each vial and in what order. From there, you go and execute the library. So you prepare your reactant and reagent stocks. The instrument's going to dose according to the recipe. The pictures I show here are actually the pictures that the instrument's using to dose out the vials. So each color represents a different reagent. So dark blue, for instance, is going to be the same, whether it's on plate 1 or plate 2. The size of the pie wedge for each vial position is going to be related to the volume being added of that reagent. All of the reagents are added, the reactions proceed, and then one thing that we've programmed into almost all of our workflows now is the instrument will automatically dose quench solution into all vials at the end point. This allows us to take the vials, stir them up, and then move them directly to UPLC mass spec for analysis. And that brings me to the last step, where we're analyzing our reaction data. The quenched vials are analyzed by UPLC mass spec. We get 144 chromatograms, which are processed partially by Empower and partially by hand, and moved into Spotfire. And so what you'll see on the right is actually the output of the screen. So the size of the circle is going to denote the relative amount of product, and then you have a grid representing all of the different conditions run. So a large circle would be the most product. High throughput screening is very powerful, but there's some limitations. First, you're limited to the number of reactions you can run in a single run. For our Freeslate deck, that's about 336 reactions in a run. And the challenge there is that you have to limit your conditions so that they only multiply out to a number equal to or less than the number of total possible reactions. And the other physical limitation, which is going to limit you far beyond 336 in many cases, is that the supply of starting materials is often limited. Imagine running even 100 reactions at 10 milligrams is a gram of material. So to run 336 reactions would be 3.3 grams of material. Oftentimes, some project labs can only spare hundreds of milligrams, but certainly less than a gram. And the outcome of these physical limitations is that you have to limit the total number of variables. A lot of times we have to assign a single temperature point to all of them so that we don't have to double the number of vials being run to allow for multiple temperatures. Because typically we'll want to design in more reagent variations rather than additional temperatures. And a lot of times it also limits the opportunities for sampling the reactions at intermediate time points. When you're running a small set, that's very practical. But on these very large sets, that's hard, especially if you go to smaller and smaller scale. And so the question that comes up is how can we generate more data without using more material? And one possible answer to that would be a feedback loop. Feedback as a synthetic chemistry tool is nothing new. We use it all the time. Manual feedback is common in lab scale chemistry. And imagine you're running a reaction in a round bottom flask. You're going to sample, you analyze by UPLC or maybe by TLC. And then depending on the results that you see, is it all converted to product? Is the reaction going very slow? You adjust the conditions. You add more reagents. You heat it up. You cool it down, depending on the reaction, the analysis that you saw. That's feedback. So the question is, what's needed to implement this kind of feedback on an automated platform? First, you have to automate reaction sampling. So how do we sample all of these reactions in an automated fashion to make it practical? Second, you have to integrate basically the bottom arrow here to have your analysis and your results go back and integrate with the system that's controlling the automated platform. And then you have to provide a mechanism for the automated platform to respond to the analysis. So how is it going to add reagents, heat, and cool? So the first part of implementing the loop is implementing reaction sampling. And so from a library studio or recipe perspective, it's a single line in our case. So we now have a command called HPLC, which will allow vials to be sampled. Because our chemistry is highly variable, much like a lot of process chemistry, we need different sampling options depending on the chemistry we're running. The simplest is actually method 3, but this is also the least commonly used, where you actually just take a sample of the reaction mixture and inject it directly onto the HPLC. This is least commonly used because oftentimes we're running a too high of concentration to do direct injection onto the HPLC. Because of these high concentrations, we have method 1 and method 2. Method 1 allows you to sample a reaction mixture, have quench solution added, dilute appropriately, and then inject that diluted mixture onto the HPLC. And then method 2 allows for serial dilution, where your reaction mixture is sampled, a larger amount of quench solution is added, that mixture is then sampled again and diluted. So you have a very low concentration solution being injected onto the HPLC. So now we have the automated system taking the samples. Now it's a question of integrating the system controlling the automation with the HPLC itself. And the folks at Freeslate have helped us connect in with our chem station. So Automation Studio, which is driving the robot, establishes a sample set on chem station, which is just your HPLC software. That reflects the library. When each sample is injected into that custom valve I showed you, a signal will be sent to your HPLC saying that an injection has been made. It's essentially a manual injection valve for your HPLC. The sample is then analyzed just like any other sample on your HPLC. We actually have chem station treating the data with and picking peaks so that you would have starting material labeled and product labeled. This data is then received by Automation Studio, the area of each peak that's relevant, the area percent of each relevant peak, and essentially Automation Studio will then calculate a ratio based on those numbers. So this is the ratio of the product area to starting material area, derived directly from the HPLC tree. The final step then of implementing the loop is your system now has analytical information. How do you respond? And the way we set this up is that the chemist will actually set high and low thresholds for the calculated ratios before the run. What that means is you say, if the ratio of product to starting material is greater than 3, that's going to be the high threshold. So we will do something with those high conversion reactions. And the low thresholds might be something like 0.2. The ratio of product to starting material is less than 0.2. We're going to do, that'll be your very low conversion reactions. And then you have your middle. So you have low, middle, and high levels now for each reaction. You'll then assign an action for each of those levels. We have 5 standard actions, the first of which is do nothing, because there's times when you just want to sample the reaction and then allow it to keep stirring at the temperature you started at. You can move the reaction to a cold plate, prevent degradation if it's high conversion, for instance. You can also move it to a hot plate, so to encourage faster reaction. You can add a reagent, or you can add a reagent and heat. But the chemist picks one of those standard actions and dials that in prior to the run so that you can make the decision based on what you know about the chemistry. It's not hard-coded into the instrument. And then essentially, as the data is received by the instrument can move the vials or add reagents based on the response. So the reaction vials would move over to hot plate or cold plate as necessary and as specified by the chemist. So let's take a look at the feedback loop all on one side. We're going to start by preparing the reagents. This is charging reagents to the vials, heating, and stirring. And then each vial from there is treated separately. After the appropriate amount of time, it's sampled, quenched, diluted automatically, and injected onto the HPLC. A response is calculated, just like we were talking about, from the peak ratio. And then the instrument will perform a response based on that ratio. If it's a low response, medium response, or high response. Then all of the reagents are then given time to stir at their new conditions, whether it's colder, hotter, or with reagents. After that period of time, the instrument will reassemble the vials, at which point the scientist can come back in and restart the loop to get endpoint samples. This is one of our limitations, which is why it's a dotted arrow, is we now have to control the restart of the loop to get the second sample. We can also look at this graphically. The reactions are prepared, and this is standard operations. This is just like the amidation screen I was talking about, where you can add reagents to your vials. After a certain amount of time, the reactions are sampled and diluted. This, again, could be sample method 1 or 2. If you're doing direct ingest, of course, you don't have HPLC vials left on the deck. One great thing about having HPLC vials containing your samples on the deck is that you can then take them to offline analysis if you need secondary analysis. For instance, if you need chiral SSD, you can take them off the deck. Let's consider the results of the reaction. The red reaction has a low response, small amount of product to a large amount of stirring material. So it was moved to the heated plate. The blue reaction has a medium response. So it falls above the low threshold, below the high threshold. So in this case, the action was reagent added. So we had yellow reagents added to our blue reaction. And then finally, you can have a reaction with a high response, similar to the green reaction, where you have a significant amount of product and a very small amount of starting material. And this would be a high response, and so the action could be moved to cold plate. At the end of the reaction, these vials are then reassembled so that you can repeat the loop and collect a second set of data to see if the exposure to new conditions helps drive the reactions further. Once we had this feedback loop established on our system, we wanted to test it with chemistry we knew. The direct formation of cyanoacetaminophen from amines and ethyl cyanoacetate had been previously studied in our lab, and we know that this reaction is catalyzed by DBU, so that it'll go very, very fast, but also other tertiary means, for instance, Phoenix base, will accelerate the reaction slightly, especially at elevated temperatures. So this made it, and this reaction is also very quick. So it made it a great test case for the feedback loop to see if we're getting the kind of data we need out of this feedback loop. And so the protocol was as follows. We charged our components at 30 degrees. The amine is the final addition because it starts the reaction. We waited 30 minutes. All of the reactions were sampleized, diluted, and analyzed by HPLC. And as those analytical results came off, logic was executed. If the product to starting material ratio was greater than 3, they were moved to a cold plate. The middle range were held at 30, and the low range were moved to 60 degrees. The reactions were then allowed to stir for an additional 4 hours, and then they were sampled, diluted, and analyzed again. So let's take a look at the first sample for all these reactions. So what you'll see is the highest levels of DBU went very quickly to high conversion. So after 30 minutes of reaction, they were at high conversion. And so those were moved to the 15-degree plate. The reaction at 0.2 equivalents of DBU was held at 30 degrees because it fell between the high and the low threshold. The 0.1 equivalent DBU reaction and all of the other tertiary amine reactions, including the control case where no additional base was added, were moved to 60 degrees because of low conversion. And what you'll see is when we took the second sample after 4 hours, all of the reactions proceeded further. The best conditions were actually the 0.1 equivalents of DBU reactions. You'll notice that there's very little difference in conversion between the 0.1 equivalent DBU reaction and the 1 equivalent DBU reaction. But what's a little more subtle here is the size of the circle here denotes the area count of product. We actually had more product present in the 0.1 equivalent DBU reaction as opposed to all of the others, implying that some degradation products were forming and consuming some of the actual product present. So essentially here, in one round of screening, we got the hint that low DBU at a slightly elevated temperature is the best condition. And this took many, many iterations of traditional screening when we were running this for Project Chemistry in the past. So this gave us a great first pass at the feedback loop to show that it's giving more data in a single screen than traditional screening. So how could you imagine applying this feedback loop to new chemistry? Right now it's limited to a single plate. So we have to realize we're talking about 48 vials or less. And so we have 2 possible use cases. The first is a feedback loop for a limited primary screen. We're limited to 48 vials, but it does add a second sample, so you automatically get 2 time points built in. And it automatically adds a temperature component, which oftentimes you can't build in if you are material limited. And so this is good for a small directed screen. So depending on your chemistry, what's already known about the chemistry, you might want to run a small screen. For instance, 4 bases and 6 catalysts. Or perhaps you have very limited starting materials. So 48 vials is as many as you can do. And this will really help us identify catalysts that are active at lower high temperatures because you have that temperature component built into the first screen. We've seen many examples where certain palladium catalysts, for instance, are very active at 50 degrees but don't work as well at 90, or the reverse case. The other possible use case is a feedback loop as a secondary screen. So first you would conduct your initial screen of hundreds to provide hits. And then you would take those hits and focus them in for the secondary screen. This would add sample data not provided in the first round, and it would add temperature components or stoichiometry variation, which wasn't available in the first round. And so you could imagine this as a follow-up on the screen of 144, just like that amidation screen I showed earlier. And this would allow variation in addition order, stoichiometry, and everything around the best hit. And then I have an example of the feedback loop being used as a secondary screen for a CDI and DBU mediated amidation. So in the screen of a carboxylic acid reacting with an aniline nucleophile, CDI was identified as an activating agent of choice in a broad primary screen, so one of hundreds, similar to the one I showed earlier. DBU is actually known to catalyze these reactions. We studied it in our lab between imidazolides and anilines. And so we planned a feedback screen to optimize around reaction time, temperature, and DBU loading. In this case, the imidazolide was generated prior to the screen and concentrated into the vials. The automated system was used to add the amine, solvent, and the DBU to each vial. The reactions were held at 50 degrees for 4 hours, sampled and analyzed, and the vials were treated at that point according to the logic. And then they were moved appropriately and held for 16 hours. At that point, the plates was reassembled and sampled a second time. I just want to point out one of the challenges when you're running this as a chemist is you have to think carefully about choosing times and temperatures where the conditions will be differentiated. You want to give the reaction long enough so it's doing something, but you don't want to go to the point where all reactions are providing you with 90% yields, because you're not going to be able to learn anything from this feedback loop. And here are the results from the CDI and DBU mediated amidation. Again, the cyan points, just as in the previous graph, are the first sample, and the dark blue points are the second sample. So what you'll see is that 1 equivalent and 1.5 equivalents of DBU, the reaction is virtually done after 4 hours at 50 degrees. Further time was unnecessary. Interestingly, all of the lower cases were proceeding significantly slower. So even though the 0.75 equivalence case fell into the middle bucket, it didn't proceed to very high conversion over the second 16 hours before the second sample. So what this points to is that the best conditions are actually the higher DBU loading with the short reaction time. So in summary, why try using feedback? And really what we think is a screen with feedback is going to generate more data than a traditional screen on a first pass. So we're getting data that would take multiple rounds of traditional screening. So less material to generate more data. That's the whole idea. And so the future directions to this feedback loop in our group are going to be application to a broader scope of reactions. And this is ongoing currently. As well as automation development, we want to develop an automated second loop so we don't have to interfere with the system or interact with the system to get that endpoint data, as well as timing optimization so that we can allow more vials to be run more quickly. And with that, I would just like to thank first my co-authors, Josh Dinette, who has been working on this project since the beginning and providing all of the analytical support, He Wang, who did a wonderful job on all our statistics analysis, and then Chris McWilliams. I would also like to thank my collaborators, Jerry, Barb, Teresa, Dave, and then from Freeslate, Peter, Jonathan, and Stephen. Thank you very much for your attention. I'd be happy to answer any of your questions.
Perfect. Thank you, Christine. Ladies and gentlemen, it's now time for the Q&A session. So if you have any questions, please continue to submit them. We've got some good questions that have already come in, and we've got around 15 minutes left of the session. So Christine will try and answer as many questions as she can. Christine, the first question that has come in is, what are the limitations to the current feedback system?
Well, there's a few different limitations. The first one, of course, is that the software right now is limited to taking a single sample from 48 reactions only. And this is a programmatic limitation. This was our first pass at the feedback loop design on both our part and Freeslate's part. And so this can potentially be fixed to allow for more samples and more reactions with changes to the programming. One of the other major limitations is the time for analysis. Right now, it takes quite a while to sample a reaction, dilute it, inject it onto the HPLC, and even with a fast HPLC method, it's still a significant amount of time to sample and analyze each vial. And we've been thinking about this. Partially, it could be a programmatic change. We can change how our wash cycles are done, how the arms are moving, which needles are being used for which actions. But also the deeper question is how can we speed up the analysis? And we've been thinking about this and brainstorming as to potential options for PAT, so perhaps Raman analysis of the vials. We've also been looking at direct injection onto mass spec, ways to make the flow paths shorter, parallel HPLC. We've been brainstorming with a number of analytical chemists on this, and so we hope to continue to develop it and make it faster.
Perfect. Thank you, Kristin. Another question that has come in is, if you see a second point that is a hit in the feedback loop after changing conditions, how do you determine whether it was the time, temperature, or reagent that drove the reaction to completion?
Okay, that's a great question, because in a traditional DOE, where you would have all of the appropriate factorial reactions, where you would have many, many reactions going, you would be immediately able to deconvolute those. Here, we have convoluted factors. And so the way you would deconvolute that is you would take the hit, and then you would run it with or without the excess reagent, with or without the excess heat to determine. So you do have to go back and rerun those reactions to deconvolute the factor that's really driving the reaction to completion. We're willing to take that hit because by using the feedback loop, we've eliminated a lot of duplicate reactions or very similar reactions. So we just run a few more after the feedback loop.
Perfect. Thank you, Kristin. We still have some questions that have come in, but I just want to let the audience know that if you have any questions and you don't want to ask them today, or questions that come to you later on after this session, please take note of Kristin's contact details on the slide in front of you. And I'm sure she'll be happy to receive some questions after today's session. The next question that has come in is, do you use an overshoot when using the multi-addition mode? This might help with the accuracy of the last dose.
Yes, we do use an overshoot volume. We make it very small. The challenge with the system is that the overshoot is hard-coded, at least the way we have our system set up, so that it's going to be the same for small and large doses. We do have one set up. Unfortunately, it has not, at this point, shown any benefit for the final dose on a multi-dose, in a multi-dose scenario.
Perfect, thank you. Another question that has come in is, for consecutive dispensing liquid, is there something particular about the 7th run, or is it that for any N dispensers, the nth file is necessarily unreliable regardless of the value of N?
Yes, it is always the nth file. It is 7th in our case because we specifically chose 7 vial blocks, so we can control that the final dispense was always in vial 7. It could be the 2nd dose, it could be the 9th dose. It all depends on whether you're pulling from the 500 microliter syringe or the 5 milliliter syringe and what your dosing volume is, but it's always the final dispense. And what you see on larger volumes actually is that oftentimes the first and last dispense can be problematic. Great question.
Perfect, thank you, Kristin. Another question that has come in is a few questions. Can the system transfer the contents of a vial if and when a reaction is judged done by LCB into a second reaction file?
I think, yes, it probably could. It would take a little bit of work from a practical standpoint because you would need to very carefully set up your syringe depth so you could pull most of your reaction mixture without interfering with your stir bar and then transfer it. But you can definitely transfer from one vial to another vial and continue to react it. Potentially, I'm guessing for a two-step reaction, that would be a possibility. It would be tough, I think, to get 100% of the volume of vial 1 into vial 2. But it could probably be done. It'd just be a technological challenge.
Thank you. Ladies and gentlemen, if you still have questions, please continue to submit them in. We have around 5 to 10 minutes to get some more questions in. So another one that's come in is, are there any ideas for moving away from having to manually restart the loop for a second sample?
Yes. That's actually a fairly straightforward programming change, but we do have to reprogram to do it. Essentially, we need to have a second plate on deck that's set up for that secondary sample. And we have not made that change yet. We'll probably need some Freeslate help to do it, but it should be fairly straightforward.
Perfect, thank you. Another question that's come in is, where in the overall development timeline do you utilize these tools, i.e. prior to the initial scale-up?
We screen reactions that are in all stages. So this tool and other high-throughput, other screening tools could be used on something as early as the first clinical batch, and it could be as late as going into manufacturing. So we see the whole range. Typically, the larger scale screens, where we're running hundreds and hundreds of vials, tend to happen as after a few batches have been run on sort of kilo lab and or pilot plant scale. So early development has happened, and there is a scaled method in place, but potentially we usually are evaluating options to change that for future scale-ups.
Excellent. Another question is, what is the speed of a 2 millimeter and 10 millimeter vial filling in CS2? How do you ensure the quality of vials?
I'm not sure I completely understand the question, but dispensing speed is very crucial to getting quality volume dispenses into vials. Typically, we don't dispense into larger vials. We only dispense into 2 milliliter vials. There are ways to build in viscosity controls. When we were doing our statistical measurements, we were actually specifically keeping the dispense speeds the same so that we could really test out the range of viscosities that would be appropriate, our sort of standard settings for dispense speeds. I don't have access currently to the exact speed of dispense. That is going to be dependent as well on the size of the syringe pump being used.
Thank you. The next question that has come in is, do you use metal hoppers or plastic hoppers?
We have both metal hoppers and plastic hoppers. In my limited experience with solid dosing on the system, I would say I've had far better results with the metal hoppers, primarily because we had problems with static and material sticking on the plastic. And that's more likely due to the solid that I was trying to dose rather than the plastic hopper itself. But I would say the choice between metal and plastic should be made based on the solids you're dosing and perhaps the amount of solid you have to dose.
Excellent, thank you. Another question is, what is the time difference between the sample analysis and correction during the operation, i.e. correction slash response time in the loop? What is the percentage rejection of end product during corrective measures?
I actually don't have any comments because I'm not exactly sure what they're asking at this point. I'd be happy to respond if that person would like to email me their question, perhaps we can talk offline.
Yeah, that's absolutely fine. Yeah, if we don't answer all the questions today, Kristin will have access to these questions later on, so I'm sure she'll be happy to try and answer any questions that she couldn't get through today. And alternatively, please feel free to take Kristin's contact details on the slide in front of you if you have questions later on. Another question that has come in is, do you use a shorts method for quick analysis?
Yes, we do use the shortest HPLC method possible because remember, in a lot of these cases, we're not looking to see every single impurity in the reaction and get super high resolution. We're really looking for a couple of C peaks. That could, in all of the examples I gave, it was starting material and product. You could imagine that it could also be a starting an internal standard and a starting material, or an internal standard and a product. We do use fairly quick methods, or as quick as we can get, on our Agilent 1100. Right now, we are limited to the Agilent 1100 because that was what it was available to put on the system.
Excellent. Well, Kristin, we've nearly come up to the hour, so if you see any questions in that questions box that you'd like to answer while we have a few minutes left, or if you have any kind of final thoughts to finish off the session, the floor is yours.
I think we can probably just wrap it up there. If anyone has questions that are still outstanding, please contact me by email. And thank you very much for listening to the webinar.
Excellent. Well, thank you, Kristin, for truly an excellent presentation, and thank you to Freeslate for sponsoring the session today. I'd also like to thank all the audience that have joined us today and for all your questions that have come in. As Kristin said, her email address is on the screen in front of you, so please feel free to contact her. And if we didn't get through to your question today, I'm sure you'll get a response in the upcoming days. Regarding kind of the slides and the recording, this will all be available at www.business-review-webinars.com, and they will be up there in the upcoming days, and you'll receive a notification as soon as they are ready. We look forward to sharing further webinars with you, so please do keep an eye out on the website I just mentioned, and follow us on Twitter at @BRWebinars, and alternatively check us out on our LinkedIn groups, Business Review Webinars. Just search that and you'll be able to find us. Thank you once again for joining us today, and I hope you all have a nice day. Goodbye.